Well, we're nearly there. Welcome back, everyone. Hopefully we get someone on the Zoom side. It just seems weird to have Zoom empty, but we'll continue as normal if that happens. Well, I think we're just about there. Yep, it's official. We're now on week 12. After this week, we're at the 75% mark. So congratulations, folks. We're really getting through it pretty quickly here. And you can see on the Moodle website that there's definitely a plan for further progress so far. This week is a big week for us because whatever we 100% complete as a chapter will inform us on the last chapter to expect on the upcoming exam 3. That's probably going to be chapter 19. Chapter 20, I think we'll likely finish when we come back on Tuesday of this week right here. So that means exam 3 is going to be covering chapters 17, that's one mean, 18, that's two means, and 19 for one proportion. So that also means this weekend is a busy one. You can expect, just like exam 1, exam 2, more parallelism on exam 3. Over this weekend, starting on Friday, going through Sunday, I'll start dumping in information along the lines of the exam 3 formula sheet. I'll have sample exam 3 exercises, 2 versions in the same kind of formats as you see here and here. And once we are complete with the exam, we'll come solve or post the solutions as before. And what else did I want to add? Let's see. It's going to say something about problems that we ourselves might have on Thursday of this week. So just like what we did on exam 2, if on Thursday of this week we have review questions relative to exam 3, don't hesitate to bring them to the class. I'll be very happy to go over whichever questions come up. But that's pretty much our plan so far. We'll do a week as normal. Tuesday is normal on this week, but then Thursday we're turning over to exam questions. So we'll finish our work at the end of those exam questions. Then on this week, it is an exam week. So that means Tuesday, we won't have class as normal. We'll be doing exams. Thursday will be a normal class, but we're just tying up our last bit of work on this section or on whatever section we're finishing up here. Then on close week, I've been informed by the university, this is a new policy that was effective last semester, but we're trying a little bit better on this semester. We're not intending to cover new material on close week. We're just finishing off any last bit of work from the prior week and moving directly into reviewing for the rest of this entire week. And just a reminder, as far as exams go, for this class, the final exam is meant to be a take-home final exam. It's going to be several questions over the entire course, over the methods that we've covered. It's going to be not like these exam questions, which are concept questions fundamentally. They'll be more like the homework questions where you're doing a full and complete analysis on a problem-by-problem basis. So that's a lot of what we'll be doing on closed week, just reviewing ourselves, preparing for what the final exam is going to look like. Then on Thursday of this week, at about the last 10 minutes of class when we're wrapping up a review, we'll unhide the final exam, which is just going to be like an assignment down here. And it will be due, I'm thinking on Thursday was my initial thought, but I think Friday just makes a little bit more sense. They'll be at the very end of the semester. So if you're thinking of the 17th Thursday as being the real due date, that's a good thought to just keep in your mind. And then think of Friday as just an additional bonus day to double check your work, get in any extra time you need to solidify your solutions. Well, any questions, folks, about the plan so far? Okay, well, we are back here, chapter 19. We covered one method on doing a confidence interval. And really the major thing that was tough about this method is they really mean it when they say large sample. We have to pass the conditions that the number of successes in the sample exceeds 15, and same with the number of failures. So this gives us a lower minimum of 30 just to run this method. But in actuality, you're probably well above 100 to have a sample size that's required to run this, especially if the true proportion is close to 0 or close to 1. So it's really restrictive. There are a lot of alternative methods, but the method that we're going to look into is going to be a 1 that is going to allow for lower values here and here, but then just widens the entire confidence interval by specifically making the standard error bigger, quite a bit bigger in certain situations. So here's what the method looks like. We briefly took a look because we're dealing with the new estimator p tilde. So p tilde widens out the confidence interval by including 4 imaginary observations into the sample. We had 2 successes, so there's a +2 on the successes side. We had 2 failures, that's why the total new sample is at +4, with the goal of taking this part, p hat times 1 minus p hat. We briefly looked into some graphing software and showed when p hat moves closer to 0.5, and it will once it's replaced by something like this whole structure gets larger, and so now we're making the confidence interval larger in that way. So this is the whole method. We just have to be careful on how to construct p tilde, how to construct the brand new standard error based off p tilde, but z star is just the same as before, and so is the interpretation. So let's put this into practice on the very next problem. Any questions or comments first? Okay, let's jump in. So here's our next problem. Example 5 is about a total hip replacement kind of a situation, which is really devastating, hard to recover from. Starts off by saying the technology underlying hip replacements has changed and operations have become more popular. In 2008, it's starting to look like really old data. There's over 250,000 hip replacements. But here's some new drama. In 2003, a new type of hip, highly durable ceramic hips, were being marketed for the total hip replacement. So they're highly durable, probably cheaper as well to run this as a procedure. But there are also other side effects. It says, unfortunately, for too many patients, increased durability has been counterbalanced, it sounds like a pun here in the writing, by an increased incidence of squeaking. So imagine your grandma has gone through a really traumatic surgery, recovery process, all that, and now every time she bends down to grab something off the floor, it squeaks. It seems funny at first, but this could be so devastating that patients may have been happier not have gone through this whole entire procedure. So this could be actually, in fact, extremely devastating to the patient. So we're interested in, well, how many of these hips starting in 2003 had this kind of problem? Goes back to the May 11th, 2008 issue. That's why they gave us data in 2008 of the New York Times reporting that in one study, it says here, 143 individuals who received ceramic hips between 2003 2005, so really constrained in that time frame, 10 of them developed squeaking. Not something you can easily fix. That's just now a lifelong situation the person likely has to go through. So we're told in this problem, sample size is 143 individuals. We're told 10 of the hips began squeaking. That's telling us the number of successes in the problem. That's what the study seems to be all about, the bad outcome for this total hip replacement. So we have 10 hips like that. That tells us these are the successes. And in our formula, we often write X to be the number of successes in the problem, capital X. It's now set at 10. So 10 individuals have squeaking hips now. And we could analyze these data as before using the large sample confidence interval, but we're immediately hit with a problem. It says in part A, explain why the conditions for the large sample confidence interval are not met. Certainly didn't say anything about randomization, but more critically, we only have 10 successes. This method, the large sample confidence interval, requires that the number of successes, we're mostly focusing on successes here because that's the low count, but let's put in parenthetical, and failures, be at least, and anyone recall what the value was for this condition to pass? Was it 10 or 15? It was 15, good call. It's honestly confusing. Let me show you why. In the actual central limit theorem, these are the conditions for the central limit theorem to be effective. A count at 10, way lower than a count at 15. That's kind of suspicious in a way. It's because if you're using the central limit theorem, either you're doing a what if analysis like down below, or more likely you're doing a hypothesis test. You're assuming a value of a population proportion, and it's a really powerful assumption to make. So anything that has a confidence interval analysis requires expected counts be at least 10. But in a confidence interval analysis, we have less information about what's going on in the problem. We want it to be at least 15. It's a higher benchmark to actually pass. So that's the value we have to hit. That's the trouble right here. The number of successes is way too low. The central limit theorem is not going to be effective at that count. And so we'll say here, since there are only 10 successes, the count 10 that we identified, conditions are not met. Which is pretty rough, right? That's what we mean by large sample confidence interval. In this particular problem, a sample size at 143, way too small. And that's kind of insane when you think about it. Probably we need to be closer into the 200s or 300s range, be really effective. Maybe more like in the 200s would be safe. So next, what we're going to do is not give up on the analysis. It's still an important problem. And there are other ways to analyze these data. If you're curious, you can now cite the binomial distribution, do something called a Fisher's exact binomial test on the same data, and get a pretty strong conclusion. But for our class, which is really just introductory in statistics, we're going to go with the other method described, the +4 confidence interval for a proportion using p tilde. It's a nice analysis as well. Only downside is we're getting a pretty wide confidence interval if we go this route. So let's give this our next attempt. Full analysis with the +4 method, kind of like using a non-parametric test when the main method conditions aren't satisfied. Any questions, folks, before we analyze these data this different way? Okay, we're trying to do a confidence interval analysis. That means we're estimating something from this problem. But if I've identified the successes, you essentially know what the parameter is as well. We're trying to estimate the number, well, let's say the proportion or percentage of successes, squeaking hips, amongst the entire population. Our population is confusing on this one because when we're talking about medical data like this, time is really major. If these hips were new, starting in 2003, the way these hips were implemented as a medical procedure is very particular amongst these years, 2003 to 2005. If we're thinking 2025, there's been a lot of changes on how this is actually implemented as a medical procedure. So for this kind of data, you have to be very mindful of the temporal component. We're constrained between those years in this analysis. Hang on, let's double check this. We received ceramic hips between that year, yes. So let's say here, for state, it might be something along the lines of, what is the percentage of all people receiving ceramic hips, just to include the temporal component, years 2003 to 2005, that began squeaking. So that's what we would like to estimate in this kind of problem. To get there, we now need a parameter and a chosen level of confidence. So let's come up on the top here. Let's walk this down as we go so we're not scrolling constantly. We have our practical question down below. Now we need the unknown parameter. Because this data is categorical, and we said, what is the percentage of? This is a good indicator that the unknown parameter itself is indicated as P, categorical data. These are pretty tricky to write, but our practice was we have to mention what the success is, and then we have to mention what the population is. A success is receiving a ceramic hip that eventually began to squeak. And the population is everyone who received them, but specifically within that time frame. So we can designate P as being the true percentage of all ceramic hips that began squeaking for hips we don't necessarily want to say installed on. Let me think about the wording on this. Let's say true percentage of all ceramic hips that began squeaking for total hip replacements in years 2003 to 2005. Probably there's a faster way to say this. So if you've got a better way to designate it, keep the same information in that sentence. That's always just totally fine. Any suggestions to include or remove anything? Any changes folks would make on that parameter? Okay, one suggestion, or not suggestion, but one question I would have on this one is, what would you all want to estimate the confidence on this one for? Should we go for low confidence, 90%? That is allowed on our method. 90% confidence is the lower bound on the +4 method. Or we could go at high confidence, say 99%. All up to you on this problem. Okay, anyone feel strongly one way or another? Yeah, go ahead.
Maybe 95%.
Let's go for that. I think that sounds great. Just like when we're picking alpha, trying to balance a type 1, type 2 error, same kind of thoughts actually apply as well to confidence as well. If you're picking 95% confidence, you're balancing a type 1, type 2 error. That seems weird. There's no hypothesis test right here, but a confidence interval analysis gives an equivalent conclusion to a two-tailed hypothesis test on the same information. So at 95% confidence, we're balancing a type 1, type 2 error, viewing it as an actual hypothesis test in the conclusion. So 0.95 is a good choice on this one. And next thing you have to do is take a look into condition checking. Once condition checking is done, we'll now go and do the actual computations of the problem. So we're now at this stage here. But what were the conditions of the +4 confidence interval? Really just two. First thing is that we have to have a sample size that is at least 10. Really low bar for that condition, right? But that's because it's trying to overcome the restrictive conditions of this analysis here. So our sample size is 143. Our sample is automatically large enough. We just have to write this in. Since n equals 143, which is greater than or equal to 10, this is the condition on passing for the +4 confidence interval method. So this right here implies, sorry, question first. Oh, let me take a look into that. I think I missed that on my conditions right here. So +4 confidence interval says to estimate true proportion P of successes, we have to have random data. So we'll mention whether we know it's random or not at the end. Confidence needs to be at least 90%. But yeah, this is kind of interesting. On the +4 method, really it's just the sample size we're worried about. Oh, gotcha, yeah. Honestly, this is what's tough about chapter 19 and chapter 20 is these counts for having a sample size large enough are very troubling or confusing because the large sample confidence interval has one benchmark we have to meet. +4 is one benchmark on just the total sample size. And the hypothesis test is different as well. That one's on expected successes and failures, both have to exceed 10. So this method, really nice on the conditions end, but we do suffer because the whole purpose is to widen the confidence interval. Our analysis does give us a pretty wide interval as a side effect here. So we're good on this end. Sample size greater than 10 implies immediately the sample size is large enough. And other thing to check is the confidence level we selected. Well, the confidence level should be below 90% as an actual bona fide condition for this method. But if you're really thinking about that, if you dropped your confidence level below 90%, that'd be weird anyways. So that'd be something weird on any method. If you gave a 70% confidence interval, you'd have to have a really good reason to do that. So this second condition isn't as major, but it is something that is definitely a requirement for the method. We say and confidence is set to 0.95, which exceeds 0.90. That 0.90 is the benchmark for meeting this condition. So from this part, this implies this means conditions are met. I mean, they're almost met. The one thing, the most important thing that we would want to know about our conditions is still an unknown. Nowhere in this write-up did it mention anything about random data, so we should mention that as well. Conditions are met, provided these 143 observations were selected randomly. So condition checking is really pretty fast. We add a lot of comments here just because it's lecture notes to kind of connect all the dots. But you're really just checking this estimate, make a comment on what you know about randomization in the problem, and the work is totally done right at that step. Way different in context when you take a look at how we did condition checking in chapters 17 and 18. That's involved. That's looking into histograms, potentially box plots, and making a lot of different judgment calls based on the sample size. So we're next doing just the computation phase of this. Any questions at this point in the analysis? Okay, here we want to really carefully take a look at whatever statements you made here on the margin at the start of the problem. First thing we're going to calculate is P tilde. P tilde, by definition, is sample size in the denominator +4. Let me center that better. Numerator is number of successes, x plus 2. So if we bring in our information at the bottom of this screen, we'll have 10 identified successes from the original data. Add 2. Original data had sample size 143. Add 4. So our P tilde is now 12/147. Next thing we need is our new standard error. But let me move this to the next page. I think we're going to need the space. Let me call this standard error P tilde, just to emphasize new formula this time, not your ordinary standard error. So we usually write standard error P hat in this situation, but in the +4 method, not a bad idea to call it standard error P tilde as a reminder. We're shifting our entire method. This becomes square root. Same structure as before. It was before P hat times 1 minus P hat. divide by n. This time it's p tilde times 1 minus p tilde, divide by n. And this is the spot I often personally make a mistake. N plus 4, in fact. That's worth highlighting right there. So if you have n plus 4 here, it should also emerge here as well. Filling in the information, if this was an exam question, you get all of your partial credit essentially on this line, even if you made a mistake on the computation. This is going to be using p tilde, 12 140 over 147, 1 minus 12 over 147, divide by n plus 4, still 147. Whenever you do a standard error write out like this, you should see parallelism of the 147 here, here, as well as the denominator down below. And the last question with the normal method, large sample confidence interval, we saw that matching pattern here, here, here as well in the standard error. So it's just a new visual way to see we're on the right track if we see those numbers coming together. Now at this stage, we're just dropping everything into a calculator. Here's what it would look like. So square root 12 147. Let me include some parentheses out of just a need to be careful. 12 147 times 1 minus 12 over 147, divide by 147. Double check the numbers. It looks like about what we have right above, exactly what we have. And this is the value we would get out. I would say there's definitely good advice on rounding for this kind of situation. Standard error in these problems is usually pretty small because sample sizes are pretty large in this context. So I would say usually for standard error, Z star and P values, we often say 4 decimal places is pretty standard. But if you're noticing lots of leading zeros, shift that to 4 significant digits would make a lot of sense in this problem. So I would start at 0.0. First significant digit is the first non-zero entry, and let's keep 4 of them. So 0.02, or excuse me, 0.0225. We can round that one down to 8. So that's our approximated standard error at pretty high accuracy. Any questions at all, folks, getting that part down? Okay, next we need our Z star. Z star will be equal to, double check our confidence level, set to 0.95 means standard error value to expect 1.9600. And these are all the components that we would want to do really any kind of confidence interval, whether it's a large sample confidence interval or the +4 confidence interval we're doing here. Get these values in, any order is just fine. Well, sort of. You definitely want to do P tilde before the standard error. They depend on each other. The next step is just put everything together. P tilde, let me put down in, let's go with blue actually. Just fixing all my color codings here. Standard error, we often highlight in green. So the method goes, not P hat this time, it'll be P tilde plus or subtract our Z star multiplied against the standard error P tilde. So now this becomes equal to, for P tilde, I'll still drop in the exact value, 12 147ths. Add subtract 1.9600. Multiplied against standard error, so this value, 0.02258. So this is going to be the last step. And upon conclusion with this one, we'll have implication that the thing we're curious about, the unknown parameter P, true percentage of ceramic hips that begin to squeak, will be constrained by tuning whichever 2 numbers we come up with. So here's our next step. back into the calculator, we're just throwing in this structure, 12,147 minus 1.9600 times 0.02258. So here's our lower bound to start. One thing I should mention is when you use the +4 method, there is a possibility that this could become negative. If that's the case, you just use your best guide and round it up rather to 0% if that ever comes out as negative. If this comes out as negative in the next chapter, because we're looking at p hat 1 minus p hat 2, that would be normal. That could happen all the time, and we wouldn't round it up to a 0. But in chapter 1 with 1 proportion, values can't actually go below 0, can't go above 1. We got pretty close on this one. Now, here we kept 4 significant digits, but now we're dealing with a percentage. I probably would just round this to the 4 decimal places, because later on I probably would convert it to a percentage, and that would be sufficient enough of places. So this would round to 0.0374. Now less than P, which is less than. Putting it at once means you really have it twice. Just call this calculation before, convert to addition, and we're about just above 12%, 0.1259. All right, we've got it, folks. That's the estimate on P. All we now need to do is give a firm conclusion. But to do that, we should recall what was P exactly. Here it is. Kind of wrote it in a long way, but this should do the job. So when we ran this whole method, we were focusing on P tilde first, the 12 over 147. That was just an estimate of P. It doesn't include the margin of error, so that's why we included Z star standard error, and now we have a whole range of values. All we have to say is what our confidence level was and what this estimate really is. So let's begin by saying with 95% confidence, it's painful to write these out twice. Sorry about that. I know that does feel redundant. I've just found that oftentimes we are way more successful in the conclude phase if we write it down as our number 1 first step. That's what's introducing the redundancy. This feels painfully redundant to you. You wrote it down really nicely on the first step. I wouldn't be too opposed if you paraphrased it a little bit on the conclusion, because you've already wrote it down once. So if you do paraphrase, try to keep some of the elements here. Definitely don't just call it P. I'll write out with 95% confidence the true percentage of ceramic hips, let's say not installed on, but how about for 2003 to 2005 procedures. Maybe that's a nicer way to say it. So the true percentage of ceramic hips that begin to squeak. We mentioned P. Now we just say what the estimate is. If you want, you can just say the true proportion. If you're going with the proportion, just carry those numbers down exactly. If you went with percentage, then you probably want to really convert these to a percentage. So this one will be is between 3.74% and 12.59%. It is a low percentage for this to occur, but now people going through this kind of procedure maybe not relevant in 2025, but around 2008, after this article came out, people would be well informed on what is the chance of something going wrong if they go for this procedure in 2008 or 2009. Again, way in the past. The ceramic hips might be the same, but the way the procedure goes probably has evolved from these years in a slightly different way. But the risk is still there. So people would have a slightly more informed choice back in the day, around 2008, 2009. Well, that's our full analysis on troubling data where the true proportion P is closer to 0, causing a sample size of 143 to not even be large enough in that situation. So P being close to 0 or close to 1 is the kind of similar situation for quantitative data being heavily skewed, requiring huge sample sizes. Well, any last questions at all, folks, before we turn to the hypothesis test analysis? Okay, so this is how we do confidence intervals. We really resolve a lot of information this way. And now, if all we want is the hypothesis test, here are the next bit of tools that's going to take us to that kind of analysis. First, we call upon the central limit theorem once again. We're using it in a hugely direct way. It's going to be used in a way that was never used in chapter 14, quantitative data, nor chapter 17, nor chapter 18. And the reason our method is so different this time is this is a one parameter description for the central limit theorem. The true population proportion P emerges both as the central value and it's part of the formula for the spread of the distribution as well. So that has humongous ramifications for us. Here, this is just a restatement of the sample sizes for central limit theorem to be effective. And example 6 is a context-less type of scenario just to show what can happen in a hypothesis test. Suppose we have a huge sample size at 1,024. In fact, this is a pretty standard sample. Polling agencies like Gallup poll that want high precision on their confidence intervals are usually going for that kind of sample size. It's going to come from a population with true proportion of successes P. But in a hypothesis test, we make a claim about P. That value 0.35 right there in formulas is often referred to as P naught, the value to be tested in the claim for the null hypothesis. But notice in the null hypothesis, we directly conclude that the unknown proportion P of successes takes on that value, that this is the reality of the population. In fact, if for every single hypothesis test we've ran, this is the first step. Assume the null hypothesis is the literal truth about our population. P is now 0.35. That means if the null hypothesis is true, we know the full specification of the sampling distribution of P hat, the statistic. We can now directly say P hat, through the central limit theorem, a direct use of it, is now distributed normally. The true mean of this normal distribution is centered at 0.35. So when we go to collect the data, we'll just find out how many standard deviations is our statistic away from the assumed central value in the central limit theorem. And then it gets even better because we can now say, we also know the exact variation of the distribution. Again, this is kind of spectacular in a way because it has never happened before as a process. This is the first time it does. The standard deviation is now 0.35, coming from right over here, times 1 minus 0.35, divide by the sample size n, and in our problem is 1,024. And I would leave it just like this on paper, because when we go to actually calculate a confidence interval or a test statistic, it's good to input this stuff just exactly like we did before to get the most accuracy we can squeeze out of the silicone over here. We've already made estimates. This is an approximation here. So we try not to make estimates on top of our estimates. So there it is. The value of P hat is directly this. There's nothing unknown about this. And so what this now implies directly is the test statistic is Z as before. We take the data that came, or excuse me, the statistic that came from the sample data, subtract from that the thing we're comparing it against in the null hypothesis, P minus 0.35. We divide it by what we would often call a standard error. In every other method, that would be true, but not here. Here we're dividing it by the exact standard deviation from the model, assuming the null hypothesis is true. Always remember this statement right here. So then what goes down below is square root 0.35 times 0.65, just to save a little space there, divide by 1,024. Don't know why I put a 5 there. And so here's the next relative comment. This whole thing goes down below there. This is the exact standard deviation. So kind of interesting in a way, we have a lot of power for hypothesis testing, and that's why the benchmark for passing is set to 10. But we have a little bit more to say about that. Let's take a look at now at the full conditions and methods. We'll be on our way with this problem here. First, any questions at the moment with finishing off example 6? Okay, so huge assumption, assuming a null hypothesis is true in this context with categorical data. Now, if we go and put down our whole methods on paper, here's what it looks like. This is the significance test for a proportion. We want a simple random sample of size n, population that contains unknown proportion p of successes. Let's start by highlighting that part and track the change on p here. So that means we'll test a null hypothesis of saying p is assigned to some supposed value, p naught, like we mentioned before. We check conditions, like before we briefly discuss if we know the sample is random. Here, we carefully check if the sample is large enough. And this is for the sake of completion. You could skip this part if you like on your discussion. All the data in this class will satisfy this by default, but something to be very mindful of. Part 2, though, is definitely kind of new. So let's just put down our usual guidance. Here we'll say, briefly discuss. On part 3, just as before, we're not required to check. This is just full awareness that the method can fail in an unusual way on part 3. And now for part 2, the thing highlighted in yellow is pretty major, actually. If we're doing a confidence interval problem, say the large sample confidence interval, we require at least 15 successes and 15 failures literally in the sample. However, this method doesn't care about how many successes or failures are in your sample. You could have all successes in your sample or nothing but failures in your sample, and it doesn't matter. The hypothesis test works if expected number of successes and expected number of failures is actually true. When we say expected number, it means the numbers we expect. When we make that humongous assumption, once again, this is what hypothesis testing is all about. Assume the null is true, see how compatible your data is with that assumption. That means the formula here is way more specific than it looks like. N times P naught means we're taking P naught coming from the null hypothesis. Just take your sample size, multiply by the hypothesized value, it has to exceed 10. That came directly out of the central limit theorem. Sample is lower because, again, that's a powerful assumption. We lose it for confidence intervals. That's why it was at 15, but for successes, failures in the sample. Then this would be the numbers of failures expected, not what's in the sample, just what we would expect to get. Take n times 1 minus p naught, has to be larger than 10. So a little bit extra space here just to mention that these computations here are different from computations, or let's say sample sizes, for the large sample confidence interval, I'll abbreviate to CI. So definitely keep those separate in your mind. For doing a hypothesis test, this is so humongously powerful that our condition checking has changed in a really, really big way. Kind of strange in that sense. In prior chapters, 17 and 18, your condition checking always was the same, whether it was a confidence interval or a hypothesis test. The type of analysis didn't inform the condition checking, but here it absolutely does. Categorical data is just weirder. So the test statistic is exactly as what we described before. Take the p-hat value that comes from the data, divide from this assumption and the null hypothesis. You're dividing by the exact standard deviations in the problem. So this is directly calculating, not as an estimate, but the exact number of standard deviations that p-hat is away from p-naught, that our actual data is away from this assumption in exact standard deviations. That last statement, exact standard deviations, is again, assuming the null hypothesis is true, a giant assumption that pretty much shadows everything on this analysis. So that's the computation of the test statistic. But then everything else, I've added a lot of space here, but it goes exactly the same as what you would have saw in chapter 14. So what we would say here for a right tail test, p bigger than p naught, would be just go p value equals p norm. So we're back in the normal distribution. This one's a right tail test, but you just grab your test statistic z. Then take z. That's pretty much it. We don't have to describe degrees of freedom. We don't have to say mean is 0, standard deviation is 1. That's the general assumption for p norm. We just have to control where the area is aggregated. Set lower.tail equals false. And I found in RStudio the other week that if you are writing out false entirely, it has to be all caps. So shouldn't forget that here either. Left tail test is even nicer. P-value is P norm Z, and then we're done on that one. Two-tail test, you have to be a little bit careful because the way you run it might depend on the actual sign value of Z, whether it's positive or negative. Or you could just write this once, include absolute value of Z, and it would look like this. For the two-tail test, p-value 2 times p-norm. Don't forget with the two-tail test, there's always a doubling factor right here. So 2 times p-norm, we can do the absolute value of Z. Now the sign of Z is irrelevant. Use this method, do lower.tail. Equals false. We're gathering now the area in the right tail, and then we're doubling it. And that would automatically do the job. If you don't want the lower.tail as false in there because you feel like it kind of looks ugly in your syntax, I totally get that. Here's another way you could go. You could just wipe that out, go negative absolute value Z, and it works exactly the same. What's doing is it's taking your Z, its absolute value, now forcing it negative on the left tail, and just doubling the area on the left tail. When we went this route, we're taking Z, forcing it positive, putting it to the right tail, getting the area on the right tail by that syntax, and then just doubling it. So either way you'd like to do this would work. But this is the way the author described it, so I'm really just focusing on the reading the book going this route. So that's the full method. Only thing new here is computation of the Z-test statistic. Everything else is going to be highly similar. Any questions at all, folks, before we try out this new method on the next problem? Okay, so here's this next problem. These data are really pretty heavy. This is a lot going on in example 6. But I think it's important to do problems like these. We've done a couple problems along these lines where it's really serious medical situations. But it just highlights the importance of this kind of statistical analysis, of being really, really careful with our data analysis. It says in example 6, in the article, prothrombotic factors in children with stroke or porencephalopathy. Let me know if I'm pronouncing any of these weird. I'll get better as we go. This is in the Pediatrics Journal. These authors compare differences and similarities in children with arterial ischemic stroke and porencephaly. That seems to indicate a population. We're interested with children struggling with those specific conditions. I don't know exactly what they are. I mean, ischemic stroke, we probably all have a great idea. I don't know exactly what that is, but we can still run through the data analysis, not being experts on these things. We would just have to hope that experts that analyze these data did it appropriately. They go on to tell us there's 3 classification categories were used. That's concerning to us because our categorical data only has 2 categories, success and failure. So if we're presented with 3 categories, we must mark one of them as a success, the other 2 as being the failures in the problem. It just makes it a little bit more tricky in identifying the success. But if you see a question mark, that's probably the research question, which is dual indicating the success in the problem all at the same time. So here's the 3 categories used in this study: perinatal stroke, delayed perinatal stroke, childhood stroke. It says 59 children. These are children with arterioischemic stroke and porencephaly. We now have a sample size. Let's write in N is 59. So of the 59 children, 25 are diagnosed with delayed perinatal stroke. That's interesting because there's 2 other categories, but it seems to suggest by that line, that's the category we're interested in, delayed perinatal stroke. The question says, do the data provide sufficient statistical evidence to conclude that delayed perinatal stroke, came up again, more evidence it's a success, does not compromise 1/3 of the cases among the 3 categories? Seems like this is what we are indicating as success, delayed perinatal stroke. If that's the case, this is also telling us X equals 25 successes. Just a reminder, success doesn't mean a good outcome, just the feature of the problem that we're most interested in looking into. So what else do we know? It says answer this question, providing a complete analysis using a hypothesis test at a 1% significance level. So this is saying, in this problem, alpha indicated by the researchers should be set to 0.01. They told us themselves that that should be that value. And this right here is essentially the alternative hypothesis. It's mentioning the successes, perinatal stroke, delayed perinatal stroke rather, and it says, does not compromise 1/3. That said a lot. When it says, does not compromise, that sounds like a 2-tailed test. It didn't say is less than 1/3 or is greater than 1/3. They're just saying, weird way to say it, they're just saying is not equal to 1/3 in a really verbose, wordy way. Because probably doctors talk like that a lot, and pediatricians are specialists, so we should be expecting that. Does not compromise 1/3 is saying P not equals 1/3, but even better, the not equals there is saying 2-tailed test. So big statement in that highlighted yellow question. At this stage, we've made no progress in actually solving the problem, but we've done a huge amount. We wanted to get down to the end goal of making a nice conclusion. We really have to absorb this kind of context. Spending a lot of time on it is the best way. For a problem containing dense information like this, terms I'm not necessarily familiar with, I personally, first time seeing a problem like this, would probably read it 4 or 5 times before I'm satisfied with the conclusion. And once I put down the conclusion, probably read it 1 more time just to make sure my conclusion really fits with what's going on, the intent of the research and everything along those lines. But now that we're there, we're ready to run through the analysis. Any volunteers for a statement of the practical question on this one? Absolutely. I'm glad you mentioned that. Just as a good reminder, as was suggested in class, you don't have to write this in yourself. You have options. You can put it in your own words, or you're always allowed, even on an exam situation, say a take-home final exam, to just indicate it this way, highlighting it all. Why not? That is the actual practical question of the problem, so we can just drop it down right there. Any questions at the moment with going that route? Okay, not every problem really directly says what the practical question is. So sometimes you might be writing down a statement, but if you copy down a statement directly from a problem verbatim, like we just did, that implies a practical question, that would be okay as well. So it doesn't always have to be an interrogative with a question mark. It could be a declarative statement. We want to estimate this, for example, that would work just fine. But now we've already wrote down the unknown parameter P once. Now we have to really write it down carefully. We have two things we need to incorporate here. What is a success? We kind of indicated it here by pointing at it with X, saying it's successes. We also need to know what the population is. It said of 59 children. Well, that came from a population. The study said that the authors compared difference and similarities in what would be a population of children with that one condition. This looks like it really is the population of the problem. So when we go down to write down the parameter, we might say P equals the population proportion. I'm mixing together whether we call it proportion or a percentage intentionally, just to signify, really up to you how you'd like to write it out. P is going to be the population proportion of the successes, but we have to write that in. Population proportion of children diagnosed with delayed perinatal stroke Now we have to pull in the population among all children with arterial ischemic stroke and porencephaly. It's starting to get kind of tongue-tied saying these things. Let's write it in fully here, and then when we go to give our full conclusion, we'll paraphrase some of these things. We might just say, among all children with these conditions, for example. So we'll say here, among all children that have, let's read in this heavy statement, arterial ischemic stroke. So two conditions simultaneously, and porencephaly. Okay, we've got P down. That's a huge statement. Now we're ready to actually write down what the test is going to be. So we've defined the unknown parameter using context. Next is null hypothesis, H naught. H naught is going to be a statement that P equals some value to be tested. How do you even find that value? It comes from the practical question of the problem. We were wanting to know if we have enough evidence to say that these children that delayed perinatal stroke does not compromise 1/3 of the cases among the three categories for these children, and that 1/3 then is the value to be tested in this problem. The null hypothesis is going to be the statement that the proportion really is 1/3. But now we're asking the research question, is it different than that value? That's the alternative hypothesis. So we will test a null against an alternative hypothesis. Now we're baking in the question itself. P not equal to 1/3. Actually, let me just put that in blue as well. Then finally, we'll say at significance level, alpha is 0.01. So this will be the process for that problem. Lots of stuff to get started on this kind of thing. But finally, condition checking is actually pretty fast. So is the methods of solving this in full. This is the heavy part, just getting through the statement of the problem, the planning phase. Any questions or comments at all, folks, getting through these portions? Okay, let's see what's going on next on the condition checking. Recall condition checking is actually quite a bit different from confidence intervals, so we need to be pretty mindful of how this goes. We don't care that there's 25 successes in the sample. It turns out to be irrelevant, and that's kind of weird about this problem. What we do care about is we pull a sample of size 59, and the null hypothesis is that p equals 1/3. How many successes would we get? Once we find that value, we'll know if we are going to meet the conditions or not. We want 10 expected successes and expected failures. This condition checking is so different. Let's actually start with a statement. When h naught, p equals 1/3 is true, forgot to color code that, the expected successes is going to be equal to, the formula provided is n times p naught. Really kind of confusing. Keep in mind, here's the true proportion p. P naught is the value just to the right, they're set equal to each other. But that's what the p naught is referring to in the formula, just the 1/3. So this will be sample size of 59 multiplied by 1/3. This looks weird because it's not going to be an integer in this problem. It doesn't even have to be. So let's do the computation and then discuss it. 59/3 is 19.6 repeating. But we really do keep that value as weird as it is. You can't run a data problem or a problem like this and get to 19.6 successes. You would get 19 or 20, for example. But when we say expected successes, what we mean is a kind of average. If we ran the study at sample size 59 repeatedly, and if this is true, then all of those studies would have, on average, that many expected successes. It's allowed to be a non-integer, it just feels weird. This is greater than or equal to 10, but at greater than or equal to 10, that's the benchmark we have to pass to say we have enough successes. So let's say here, there are enough expected successes. Next, we just check if the expected failures is enough as well. So here's the next part. Also, the expected failures is going to be equal to, I've always questioned this formula because it looks weird to me. It works, but it's n times 1 minus p naught. What's weird to me about this formula, the author, just about every textbook covers, is that that's doing this in a harder way. Once you've found the expected successes, go your sample size and just subtract it off. So another formula that you could run here is just going to be n minus n times p naught, which is the value just found, 19.6. Let's run it both ways just to get a feel for that. If I took 59 minus 19.6, then I'm expecting 39.4, or 3 repeating if I did approximate here, failures. Let's run it through the formula. This is our author's way of indicating this. We'd be putting in 59 for the sample size, 1 minus 1/3, or just 2/3 if you prefer, for the proportion for failures, and then go 59 times 1 minus 1/3, and we get the 39.3 repeating on that one. Or we would have had just before if you did the subtraction route. Either way that makes most sense to you is totally fine. Let's put 39 0.3 repeating. This is also greater than or equal to 10. Putting that bit right there is wise because it's reminding your brain that's the benchmark we had to cross to get a large enough sample size. And we're emphasizing it a lot because those numbers change a lot based on the method. Confidence interval method is a totally different estimate. So this is greater than or equal to 10, which means there are enough expected failures. This means the sample size really was large enough at 59 for this particular problem. So we're ready to run through the data. We just hope this was actually random data. What they tell us about the sample? Well, it was in the pediatrics journal, so we're hoping for randomization. It would have been rejected otherwise, but that's not enough for us to be absolutely certain the data was random. They didn't say anything in this problem. They just said of the 59 children that were used in the study. So we'll just conclude our condition checking by saying conditions are met, provided the sample is random. Just a brief way to say the sample was randomly selected and used in the study. Well, condition checking is done. Now we go to the maybe slightly more fun phase of doing the computations. Any last questions, folks, about running through conditions on this one? Okay, let's next do the computations. We really need just two things here. We need a test statistic and we need a p-value. For the test statistic, we're going to need some of this information, but it would also help if we had this as well. So let's pull this in. Hard to know where to put it. Let's just jam it in right there and start computing some stuff. First thing we want to do in this is always the test statistic first, then the p-value. So start by writing out z. Here's our test statistic. It's defined to be p hat, subtract away p naught, and then divide by square root p naught. 1 minus p naught, division by n. So we have just about everything we have on paper, but you might have noticed we haven't even calculated the statistic yet after all of this work. So let's begin by computation of p hat over here on the right. P hat is number of successes x divided by sample size. In the sample, we were told that there was 25 successes. Divide by that sample size, 59. And you know what, I'll leave it in this format as well, just keeping the more exact value. So with p hat pulled in, down below we can rewrite z as being 25/59. While I fix my penmanship, there we go. Minus the value p naught comes directly out of the null hypothesis way down here. So it's the 1/3 value. And that's the logic of hypothesis testing. Measure the distance between your sample data in green with a hypothesized value, the 1/3 here in blue, in terms of either the number of approximate standard deviations, but this time it's the exact standard deviations. We'll go square root. For this value, it'll be a 1/3. 1 minus p naught is 1 minus 1/3, or just 2/3 altogether. This is then divided by, sorry, just fixing my notation here. This is all divided by the sample size n, and in this problem, n was 59. And that's our test statistic z. Let me get some space down here. We'll jam that into the calculator, get a value out. And this again is telling us the number of standard deviations away. So up in the numerator, 25/59 minus 1/3. divide by, carefully type in this part, square root 1/3 times 2/3 divided by 59. Let me double check the structure. 1/3 times 2/3 times 59. And I have two open parentheses. No, three really open. Close one, close two here. And that should be the third one. That should look right. Oh, I got a problem with my number of parentheses. Let's see here. Maybe that's better. Yeah, I've just had some trouble with parentheses. That's a lot to look into with your eyes. So now this one to 4 decimal places is 1.4729. That's not a lot of standard deviations. It looks like the sample data in green really is pretty compatible with the statement of null hypothesis, but we still need a p-value. So here's the p-value step. The p-value is going to be 2 times p-norm. Our syntax said take the absolute value of this, but once we observe it's positive, we don't need to run that portion. We'll just go 1.4729 lower dot tail, set it to false. So this will give us a p-value immediately to double check. Don't forget the 2 times right there. That's an easy thing to miss on this kind of process. So last bit on this one, start with 2 times, now p-norm, plug in your test statistic, 1.4729, lower dot tail, control that by setting it false. And now we've got a p-value. It's pretty large. We might have detected that by looking at the test statistic not being very large itself. So to 4 decimal places, 1.1408. Said that in a weird way. It's 0.1408. What we do is immediately compare that against the significance level alpha. This is bigger than or equal to 0.01. This is the condition at which we fail to reject the null hypothesis greater than or equal to significance level alpha, which means that informs us on how to conclude the whole entire problem. Looks like what we really spent the most time on was setting it up, checking conditions. This phase of the process took us about 2 or 3 minutes, it looks like, by the clock. Well, we did not have significant statistical data to support that hypothesis. We still don't assume the null hypothesis is true, so we have to be mindful of our conclusion. Our conclusion is that we just didn't have enough evidence to support the alternative. So we might say it in this way. This study does not or fails to provide significant statistical evidence. And if you like citing the alpha value, like we mentioned last class, we could cite it here as well. I'll do it in a parenthetical, but this would be optional if you'd like to or not. I'll say here at the 1%, we're talking about alpha now, significance level. To support the claim that, now we go back here, read out P not equal to 1/3, but we have to mention it with the context. And that's why we were careful writing out this P the first time. Now, again, it's painful to write out every element of there twice verbatim. So here's where we'll take a little bit of a paraphrase approach to support the claim that the proportion, I'll say population proportion, of children diagnosed with this condition, when I said this condition, I'm referring to the already defined delayed perinatal stroke. Among all children, that have, I should say this part at least, arterial ischemic stroke, and porencephaly, I was going to try to paraphrase this more, but I don't think I shortened it up as much to support the claim that this proportion is not 1/3. It's where it finally gets tied off. Sorry for running past our allotted time there, about half a minute over on this one, but that's where the study would finally end. So what does this mean for the doctors? Doesn't mean this is true. It's just that we don't have very much evidence against it at the moment. So in that case, they could continue to operate, or not operate, but work with these children that have that condition in the same kind of way as they've done before, until maybe the test is read again at higher sample size, and they do get evidence it really is different than 1/3. They would then want to know how different. Is it very far off, or is it very close? They have to make a lot of judgment calls, but this is getting them closer by giving a strong conclusion along these lines. But any last questions or comments, folks, before we call it a day officially? Okay, we've concluded the chapter 19 notes. Again, sorry for running over the minute on that one. That's something that we've been told to try to avoid at all costs. But when we come back next class, we'll be starting our chapter 20 methods. Really same stuff, but two proportions on the table that time. But I've kept you long enough. Have a great afternoon, folks, and I'll see you all in Thursday's class. Thanks, you too.